Assalamu alaikum, dear students. We're back with another video lesson. In the previous video lesson, we did talk about the root mean square values for current and for the potential difference as well. And of course, we did talk about a lot of the things, and this is where we stopped. Okay. Now, so remember the equations that we've covered in the other session. Yeah. So because we're going to need them here for the purpose of solving these questions. Okay. So it says a toaster is plugged into a source of alternating electromotive force with a root mean square value of 110 volts. The heating element is designed to convey a current with, or you can say with a peak value of 10.5 amperes. Find the following. Before we do find the following, remember this. It says a peak value. What does a peak value mean? Of course, peak value means maximum. Imagine, let's say we're talking about sinusoidal wave, yeah? So remember, it's something like the peak of a mountain. So that is the maximum point, let's say, on that wave. Maximum point on that wave, that is basically called a peak value. So this peak value, or this 10.5 ampere, is basically the maximum current here. Okay, so find the following. The root mean square in the heating element, and then of course the resistance of the heating element as well. So in order to find the root mean square current in the heating element, and of course we did talk about this one here, so we can say I effective here equals to I max over the square root of 2. So as simple as this is. And then as for the second part here, says the resistance of the heating element. In order to find the resistance here, we need both the current and the voltage here. But remember this, what I have is the root mean square value for the voltage, you can say. That is the same as V effective. So I have I effective as well. So I can simply find the resistance here. That is going to be V effective over I effective. That is 110 volt divided by this value, which is basically 7.42. 7.42. And of course, now you can find the answer, which is going to be 14 ohms of resistance, you can say. Now, second question says, which is basically the same as the previous one. I believe you could just do this one on your own. Just plug in the numbers, you'll find everything that you need to. And this is the same idea. I believe it's just the application of the equation. So pretty much you can do these pretty much. Okay, now take a look at this one. This is the same as the other one. It says the largest electromotive force. That means maximum voltage, yeah? Placed can be, or you can say can be placed across a certain capacitor, let's say at an instant is this much, yeah? So this is Vmax, you can say, what is the largest root mean square? So basically find V effective on that capacitor, you can say. So V effective equal to Vmax over the square root of 2, you just plug in numbers and that's it. All right, now another question which is very similar to what we have done so far, you can solve this one on your own as much. I believe this is pretty much the same. There's no idea in these questions. You just plug in the numbers into the equations. Of course, you will find them. There's one more thing which is perhaps a little bit, let's say, new compared to the other one. Here we have power. Don't forget, yeah? It says or asks us for the power. Remember, whenever it comes to power, you have to find power in terms of, let's say, effective values here. So basically, we have I effective, and of course, you do have the resistance here. So you can simply say power equals to I effective squared times the resistance. Using this, of course, it tells you how much power is consumed, or it could be dissipated to you. So what? How much power does the light bulb use? Basically, that is the power consumption, you can say. All right, which quantities change when alternating currents are generated? So we said there are some values that doesn't change. Yeah? So which quantities change when alternating currents are generated? Maximum current, these are, we said, it doesn't change. Current frequency, so the frequency also doesn't change. Maximum voltage doesn't change, but what it changes is the instantaneous values, because it is a sine wave. So it starts from 0, let's increase up to maximum, then decreases to 0, and then maximum negative, and then 0 again. So of course the instantaneous value has a different value at every instant. So that is D is going to be the correct answer. All right, which quantities remain constant, so it doesn't change when alternating currents are generated? You can say maximum value of current doesn't change, frequency doesn't change, maximum value of potential difference doesn't change. So we can say all of them does not change. That is going to be option D here. Okay, now take a look at this one here. It says the power dissipated in AC circuit equals to what of the power dissipated in DC? We said the power dissipated in AC is half of the power dissipated in DC, which is going to be option A here. but wait, yes, that is correct, yeah? But there's one more thing, let me tell you this one as well, right? There's this one here. We said the power dissipated, let's zoom out this one here so we can write at the sides. Watch this. The power that is, let's say the power that is dissipated, we said, in AC, okay, equals to half of the power that is dissipated in DC. What happens if I cross multiply, or just take this one here? So we can say the power that is dissipated in DC here, right, in DC equals to twice than the power that is dissipated in an AC here. So you have to be aware of this one as well. The power dissipated in DC, it is 2 times the power dissipated in AC. But the equation, or what we have learned, we just say the power dissipated in AC is half of the power dissipated in DC. If we make the DC the subject, then of course DC is going to be 2 times the AC here. Okay, and of course there is more. The average value of the alternating current on one cycle, something also very important here, says the average value of the alternating current at one cycle equals to what? Does it equal to maximum value of the current? Does it equal to half of the maximum? Does it equal to quarter of the maximum? So remember this, the average value of the alternating current at one cycle, it is going to equal to 0. Why? For example, let's say this is let's say in one complete cycle. So if this is positive 10, this is negative 10. So once you find the average, of course, you get a 0 or 0 as a total here. Okay, so this is basically what happens here, which is basically the average value for the alternating current is equal to 0 amperes, or just 0. All right, now we've set for this one as well in a ground fault interrupter, GFI, that is the difference in current across the outlet would be measured in terms of the, is it root mean square or the instantaneous values? Of course, it's going to be the root mean square values, or you can say the effective values. That is also correct. All of the following statement about the AC root mean square value and maximum values are true, except then which one of these? Yeah, we can say the root mean square value is always less than the maximum value. That is true, yeah, because if you remember the drawing, we said that, or the sinusoidal wave, we said if this is, let's say, the AC, let's just make this one nicer for now. No. Okay. Let me just go back to this. All right. So watch this. All right, this is what it is. Let's say this is maximum value. This is, you can say 0, and this is, of course, maximum, negative, and all that. We said the root mean square value is going to be somewhere right here, yeah? So if this is max, let's say I max, yeah? This is going to be I effective, you can say this red one here. So what are the questions? It says, root mean square values are always less than the maximum value. So it is true. Here's maximum. They are below the maximum. That is correct, yeah? So root mean square values are 70% of the maximum value. That is also correct. We can say, I don't know if I've mentioned that or not, but it is about, we can say a little bit more than 2/3 of the maximum. So of course, if you convert a little bit more than 2/3 into percentage, of course, you get about 70%, okay? So that is also correct here, you can say. Root mean square values are different from maximum values because the alternating current is at maximum only for an instant. That is also true. What about this one? It says root mean square values may equal maximum values. And this is incorrect. Why? Because they are always less than the maximum here. So of course, they may not equal to the maximum value. So the wrong answer here, or you can say, the one that is incorrect is option D here. All right, and of course you can see the rest. These are all equal. But let me tell you one more thing here, guys. It says an AC generator has a maximum output of 110 times the square root of 2 volt. Yeah, find the root mean square current in the circuit when the generator is connected to a 55 ohm resistor here. Now, how do we solve this one here? Okay, remember this. We have maximum output voltage, okay, but it asks for the root mean square current, okay. So how do we do this one? Well, remember this. This basically I normally call these a two-step question here. So first of all, we're going to find, you might just say current equals to what? Current equals to, we do know that current equals to, or let's be more precise with this. We do know that resistance, or using Ohm's law, R equals to V over I. We do know that, yeah? So you might just go ahead and write this value here, let's say 110, let's say times square root of 2, let's say, and then divided by 50. We want the, okay, let's go back a little bit more, yeah? We want the current. So current equals to, let's say, V over R. This is, you might just go ahead and do this one right here, 110, not 15. I don't know what is wrong today, but inshallah things will end up well. So this is 10 times the square root of 2, and then divided by, you might, this, once again, you might just use this one, but this is incorrect, guys. Why is it incorrect? We said, whatever the value is, you're going to use the same one there, so not this one here. So if you're going to use V and, or the one before this, let's say, if we're going to use this one here, we will not this one. Remember, we said whatever you're using for R, it has to be the same thing, guys. What I have here is V maximum here, right? And what I want to find is V effective, or the root mean square. Can I use maximum with I effective? No, okay? So I need to change, because the question is about I effective, so I need to find V effective first. And how do I find V effective? We do know that V effective, so let me clean the board a little. All right, so let me clean all this. We do know that, we do know that V effective equal to V max over the square root of 2, correct? Yes. So now the answer, or for this, is going to be 110 times the square root of 2 divided by the square root of 2. These square roots, of course, will cancel out. So now V effective is going to be 110 volt. Now I can use or plug this into the equation. I can say I effective equals to, right, V effective over I effective, V effective over the resistance here. So V effective is 110, that is in volt, and then the resistance is, what is the resistance? 55? Okay, so 110 divided by 55, that is going to be 2 amperes. And that is the correct answer. So you might fall for this trick, okay? Make sure that you know what it is. Remember, we cannot use V maximum with I effective, yeah? If it is, we have to use V effective with I effective, then we can use that. So if you see something like this, convert V effective to convert V maximum to V effective, then divide by, let's say, I effective, then you can make I the subject, then you can find the effective current there. So this is also a very good question in terms to see that you shouldn't fall for any of these tricks. Okay. Now, watch this one here. It says, by what factor do you multiply the maximum electromotive force calculated by the, or calculate, to calculate the root mean square effective, or for an alternating current here? So watch this. We said, what is the question? By what factor do you multiply, not divide, the maximum electromotive force to calculate the root mean square value for an alternating current? So if I want to find the root mean square, or effective, we said, all right, we will normally, here's the equation that we use. We'll say I max divided by what? By the square root of 2. But remember, if you're just going to say square root of 2, that is incorrect, because the question doesn't say divide, it says you multiply. So if we're going to do this one, we'll say root mean square is equal to, remember, what factor? So if I move this one aside, what will be this one? It's going to be a factor of 1 over the square root of 2. That is the factor, then multiplied by I maximum. So we're going to multiply I maximum by 1 over the square root of 2, which is option C here, and multiply by I maximum. Then I can get I root mean square, or I effective, you can call it. Okay, and then let's do one more here. Question 10, that is also interesting. It says, the effective value for the potential difference of AC source is 10 volt, and its frequency is 50. The equation of it is instantaneous potential difference is what? Once again, guys, what is given here is the effective value for the voltage here, for the potential difference. The equation that I have, let's say, these are all the instantaneous, the instantaneous value. Yeah? So instantaneous value equals to V max, okay, and then multiplied by sine omega t here, yes? And by the way, if omega is not given, omega equals to 2 pi f, yeah? So now what we're given here is basically the frequency is 50. So 2 times, you can say 2 times 50, that is 100 pi, yeah? So this is 100 pi and this is 100 pi. So these are, A and B are incorrect. So I'm left with two options. So it is either going to be C or D. But which one of them is correct? Yet I don't know. But watch this one here. The next thing you need to do is remember the equation says V max, but what is given here is V effective. Can I use V effective instead of V max? That is incorrect. So how can I find V max? We'll say V effective equal to V max over the square root of 2. Or if you want to find V effective, we'll say V effective equal to V max times the square root of 2, which is basically 10 times the square root of 2. And then, of course, you can plug it into this equation. Which one is 10 square root of 2? That is option D. So we'll say option D is the correct answer here. All right. And then the last one says an AC source of instantaneous value is 200 sine 314t, in which V is in volt and T is in second. What is the effective electromotive force of the source? How do you find, by the way, how do you find the effective? Yeah, we do know that if you have an equation like this, we said this part represents V maximum. So if you have V maximum, can you find the V effective? Yes. Okay, we'll say V effective equals to V max over the square root of 2, right? Which in this case, obviously, it is going to 200, or going to be 200 divided by the square root of 2. All right, so you do the math, of course, you'll find this one there. Okay, so how about we do the math and see which one it is? Okay, so we have 200, that is V maximum, divided by the square root of 2. So 200 divided by the square root of 2, the answer is going to be 141.4, so this is going to be option D. Yeah, so you might just go ahead with 200 square root of 2, right? That is incorrect. So once again, you really have to be careful if you're willing to get 100. Okay. Now let's talk about a new concept here, and that is applying Ohm's law to AC circuits, you can say, yeah? So we have, you see, when we say using Ohm's law to AC circuits, imagine or consider that we have a circuit, and this circuit, the only thing that this circuit has, you can say, or let's say the component that could consume electrical energy is this resistor here. So we have an alternating current, that is for this, and of course we have an ammeter that measures the whole current that is flowing through the circuit, and there is this voltmeter here that measures the voltage across this resistor here. Okay, so what is, and of course we have a pure resistance circuit. When we have only a resistor in a circuit, then that is called a pure resistor circuit. A circuit with only a resistance, nothing else. Okay, so how do we consider or define this? We'll say a resistor with no self-inductance, all right? When we say a resistor with no self-inductance, that means there's no inductance here. You can say it's just resistance, there's no magnetic field induced, no so whatever, and all that. And of course, we do know that resistance, or the resistance is measured in ohms, yeah? Okay, and of course, this is pretty obvious to you. Now, what are the properties of this circuit that you will see here? All right, now, remember this. The moment you connect the circuit or you turn, let's say that you close the switch, what do you notice that? You notice that electrical current will pass through the resistor, yeah? And when this happens, you can see that this ammeter, of course, where this value of the ammeter is going to rise. That means it's going to, indicating that a current is flowing through the circuit and is increasing here. At the same moment, you would see that the same thing happens with the voltage here, or with the voltmeter. Okay, that means there is a potential difference across this component. This potential difference, of course, or less coming, of course, from the source here, meaning that, let's say, the current and the voltage over this component are increasing here. Okay, so we can say, or based on that, we can say, well, let's just go through the detail. Perhaps you want to know. There are some things we need to know regarding the angle between the two, or you can say the phase difference, or the angle in, let's say, the phase angle difference between the current and the voltage. We can say 0 because they both increase together, decrease together, indicating that the phase difference between the two is 0. Okay, now, remember this, the property of a pure resistance circuit, these are the properties, very important, right? The reading of the voltmeter and the ammeter increases and decreases together, like I said, indicating that the phase difference between the two is 0. The current and the potential difference are in phase, that means there's no phase difference between the two. And then, of course, we can say, or before that, let me draw let's say this sinusoidal wave for, actually we can just explain it here. So if this is for the function of, you can say, voltage and current, let's say with the time here, so this is for current and voltage. You can see here, when the voltage is 0, the current is 0 as well. So when the voltage increases, the current increases as well. When the voltage is maximum, the current is maximum. When they both decrease and become 0 and 0, yeah, until it becomes maximum, but in you can say negative direction, that is also maximum, and of course 0, 0. So you can see here these two together, they both increase together and decrease together, indicating that the phase difference between the two is 0. And if I want to draw the phase difference for you here, you can say, or you can see this one too here, you can see if this is the current, and of course this is the voltage here, all right, you can see that there is no phase difference between, or no angle between the two here. Okay, so what about the third one here? The resistance of the ohmic resistor is independent of the frequency of the source here. So we can see that whether the frequency of the source is increasing or decreasing, that does not affect the resistance of the resistor here. And of course, the other thing you can say, this circuit, of course, it obeys Ohm's law. Okay, now, something more important now, how we can use this, or before that, let's say, before getting into the equations, let me walk you through this one as well. You can see that the current and the potential difference across a resistor and AC circuit are in phase. And of course, we have VR and IR. These are representing instantaneous values as a function of time. You can see that is, we're talking about this one here. And then for B here, you can see the phasor representation of instantaneous value for current, and then for the voltage, where VR is given in terms of, let's say, IR by the relation VR equal to IR and resistance. What are these basically? We can say, remember this, we did talk about instantaneous values before, yeah? So we said instantaneous values basically equals to what? For current, let's say, equal to I max, and of course sine omega t, yeah? That is one thing we did here. So now we're going to, instead of just writing this one here, we're just going to write, let's say, I sub r here. Let's clean this here. All right, so we're going to give it an R. What does this one mean? That means the instantaneous value for current for a circuit that has a pure resistor only. That is the above circuit. Okay, and then what about for the instantaneous value for the voltage? It is the same thing. We give it, or we'll say V sub R, indicating that the instantaneous voltage for a circuit that has a pure resistor equals to V maximum sine omega t for current I maximum sine omega t here. Okay, now, what about for, how do you find the resistance, okay? Now, regarding the resistance, as you can see here, we've already mentioned that resistance equal to what? Equals to voltage over the current. But you have to be very careful here. When we say voltage, like we've mentioned before, if you're going to use V effective, it has to be I effective as well. If we're going to use, let's say, V maximum, it has to be I maximum as well. And of course, if you're going to use V instantaneous, for a pure resistor circuit, you'll have to use the current that is, let's say, that is on the circuit as well. Or you can just say the instantaneous current for a pure resistor circuit as well. So we can use each one of these to find the resistor, the resistance of the resistor, let's say, yeah? But remember this, it has to be effective with effective, maximum with maximum, or instantaneous with instantaneous. You cannot use two different things here. It has to be all the same. Okay. Excuse me. Sorry. And then if heat energy is mentioned, now there's something else which is also very important I need to mention for you. If heat energy is mentioned, what do we do? If it talks about energy, let's say, no, not this one. Well, maybe I can do it to here. Okay, remember this, whenever heat energy is mentioned, I think I'm losing my voice. Okay, that's interesting. So remember, if heat energy is mentioned, that means power is dissipated or energy is converted to thermal energy, perhaps. Yeah, so we'll say energy normally. You do know what is energy equal to? Energy equal to power times the time. You agree with me on that, yeah? But remember, power here can be found in multiple ways, yeah? So we can say power equal to I squared. By the way, these are all effective. You have to use effective values, yeah? Okay, because that's almost like how much power constantly is being dissipated, as if it is, for example, a DC circuit, let's say. So I squared times the radius, that is 1, or power could equal to V squared, that is again effective over the radius, or it could be power, these are all effective by the way, I effective times V effective as well. So we can use these into this equation. So instead of power, now I can say energy is equal to I effective squared times radius and then multiplied by the time. Okay, I'm putting this in a bracket so that these are all for the power. And then we can use another equation. We can say V effective square over the radius multiplied by the time taken, or the time, yeah? And then the last one here, we can say energy, that is basically the energy that is transferred. It could be dissipated, whatever the type of energy is, or it could be used by the device, the component. We can say I effective multiplied by V effective multiplied by the time as well. Let me write the time better. All right, so these are the equations that we are going to use in terms of the power. So normally power equal to energy equal to power times the time. And then we have 3 equations for the power. We can substitute each one of these two into the equation as you see. All right. So moving on, we have an equation. That is a sample problem, not an equation. What does it say? It says an electrical heater operates under potential difference of Vmax is 282.8 volt. If the resistance of the heater is 500 ohms, let's scroll this up a little. Calculate the generated heat energy. So remember we said whenever heat energy is mentioned, use the following equations, the one that we've just went through, yeah? So heat energy is mentioned here, so remember those equations. If the current runs in the heater for half an hour, right, and you do know that half an hour is 30 minutes, or you can just say 0.5 of an hour, yeah? Of course, that is going to be easier to convert to seconds, so just 0.5 times 3,600. Okay, and then says what is the effective value for the current? Use the square root of 2 as 1.414. Okay, let's do this one. All right, let's do this. Okay, let's scroll this one down because we need this one. All right, so let's quickly write the information. That is Vmax. All right, Vmax equals to 282.8, that is in volt. The resistance of the heater, so resistance is 500, that is in ohms. And then calculate the generated heat, so find heat energy, okay? And if the current runs in the heater for, so we can say the time, or delta T, is half an hour. And of course, we can convert this one to seconds immediately. Half an hour multiplied by 3,600, and of course that gives us something. All right, so what is the effective value for the current as well? Yeah, so we have basically 2 questions. What is the effective value for the current as well? All right, so watch this. I have Vmax and I have the resistance, okay, and then I have the delta T. Can I find the energy here? So of course energy equals to power times the time, correct? So, but do I have the power directly? No. So what else can I use for the power? I can use the Vmax and of course, but not Vmax, guys. Remember we said we're going to use effective values for the power. So I almost forgot or fall for this one here. So how do we find V effective here? We'll say V effective, perhaps I'll do it here. All right, so V effective. So V effective equal to what? Equal to Vmax over the square root of 2 here. So what is Vmax? Vmax is 282.8 divided by what? Divided by square root of 2. So let's find the value for V effective. Yes, let's get a calculator. 282.8 divided by the square root of 2. So the answer is going to be 199.96. All right, which we can round it up to 200. 200 what? 200 volts here. Okay, you can go by with 199.9 as well, 96 and all that, but of course I'm going to round it up to 200 volt in here. Now, of course, that is V effective, okay? That is V effective, don't forget. Now I can say power equals to V effective squared over the radius times the time here. Okay, so V effective now, let's say it is 200 squared divided by the resistance, which is 500, and then multiplied by half an hour times 3,600. What is 0.5 times 3,600? It is going to be 1,800. Now you do the math, of course, you'll find the answer here. So we'll say 200 squared all right, and then multiplied by 18 and then divided by 5, let's say. So of course the answer is going to be 144,000 joules, yeah? So of course I can say, instead of saying 1,000, I can just say 144 kilojoules as well. Remember, because this is in, or it is in edges, of course, we're going to find this one in joules. What about the second part of the question? How do we find I effective? Remember, we have V effective, okay, and we have the resistance. Can I find I effective? Yes. So we'll say resistance equal to, this is a different color. So we can say resistance equals to V effective over I effective. So I want the current, so I effective equals to V effective over the resistance here. V effective was, we'll say it, about 200, and then divided by the resistance, which is 500, yeah? So of course that is 2 divided by 5 is going to be 0.4 amperes, and that is I effective, okay? So this is how you can do these or answer these questions. Okay. All right, so of course you can see each one of these values that are mentioned there. Okay, let's do one more or a few more questions here. By the way, this is pretty much very similar to what we have done so far, so I'll leave that one on you. We have a resistance and we have effective values and all that. So you're going to find I effective, and then using I effective you can find I maximum as well. So pretty much just rearranging the equation and using the equation. What about this one here? It says if the frequency of the source in item 1 or the previous question is 50 hertz, write down an expression of the instantaneous current and the potential difference across the resistor. Now I'll do this one, even though this might not be something new to you, but we'll just do it, okay, together. Okay, so what are the information? What is the information that is given? Let's say. It says the frequency. Well, what are the information? Yeah. So I think it has to be with the S. Okay. So the information that is given, we can say we're given frequency, which is 50 hertz. Let's change this color. We don't want to use red always. Okay. So let's convert this one to black. All right, so the frequency that is given is 50 hertz. Okay, what else is given? And then the previous information that were given, of course, you can do that as well. Yeah. So let me tell you what is the instantaneous, what is the instantaneous current and potential difference. For instantaneous current, by the way, right, is basically equal to I max, correct? And then, of course, sine omega t. Okay, and then for V, all right, let's write it a little bit down. So for V effect, I mean, you can say V instantaneous, of course. These are basically for pure resistance here. You can say, you can write these R's or you can leave them without. So that is V max sine omega t here. Okay, so that is basically what we have. Now, so what are the things we need here? We're given frequency. Instead of frequency, of course, we can write 2 pi f. Okay, so in this case here, instead of the omega, you can say. So now we can say 2 pi f or 2 pi times 50. 2 times 50 times pi, that is 100. So instead of this one, I can write 100 pi t here. Okay, that is this. And of course, the same thing here before I forget, because these are the same thing. So 100 pi times the t here. Now what I need to do is find I maximum and V maximum. And of course, we did find I effective and V effective in the previous question. So of course, we can say I effective equal to I max over the square root of 2. So in this case, we'll say I max equals to square root of 2 multiplied by I effective. So find the I effective, you can plug it into the equation, and then of course you can write it here. And then as for V effective, right, equals to V max over the square root of 2. Once again, V effective equals to, let's erase this one. Okay, so now we can say V max equals to, or V effective V max over the square root of 2. We want V max. Okay, so V max equals to square root of 2 multiplied by V effective. And of course, once again, get the answer from the previous question and then plug it into here. You'll find the answer. Once you find the answer, and then of course you can plug it into this one right here, and then of course you will find the answer. So as you can see here, these are basically I effective, you can say this, and of course the maximum value. Did we have the maximum value there? Oh, we did find it, yeah? So of course, that means you can just plug the numbers into there. I thought we had V effective, yeah? And then, but even better, yeah? Remember this, these are because you have them, so you don't need the conversions. And if you have I max and V max, you just plug it into the equation. But if you don't have them, you'll find it the way that I just told you how to find it. And of course, this one is easy enough. Calculate the dissipated energy in item 2 during 5 minutes, yeah? So we do have, let's say, the effective value for current, we do have the resistance, and now you're given the time. Using all this, you can find the dissipated energy. All right, now let's take a look at these mosaic questions. It says, if a pure resistance is connected alone across an AC source, the phase angle difference, or the phase difference angle between the potential difference and the current is what? So remember this, we have a circuit, and we only have a pure resistor. So what is the phase difference angle between the voltage and the current? We said it is 0. Okay, and then another question says an electrical heater operates in this and that. This is the same as what we have studied before. Now question 3 here says, in an AC circuit, which of the following does not depend on the frequency of the voltage? That is, of course, the resistor. I don't know if I've mentioned or not, but remember, I did mention, yeah? So the resistance of a resistor does not depend on the frequency, okay? So you can see here, out of all this, only resistance does not depend on the frequency of the voltage. Later on, we're going to study those, of course, the inductive, or you can say, these are, of course, will depend on the frequency, okay? And of course, we have inductive impedance and capacitive impedance, or just impedance as well, yeah? So these are all three would depend on the frequency, except then this one. Okay, and of course, what about this one here? Question 4 says, an AC is made up of a source and a resistor of pure resistance. If the frequency of the voltage increases, watch this. If the frequency of the voltage increases in the circuit, the value of the pure resistance, what will it happen? Of course, it doesn't change. Why? Because we said the resistance does not depend on the frequency. And you do know how to solve these ones. And of course, this is pretty much the same as what I have told you yet. What does it say? We have a resistance, we have effective potential difference. The frequency is 50. Says which of the following equations correctly the instantaneous current. So remember, there's two things to remember real quick, yeah? This is basically the frequency. In order, omega equals to 2 pi f, yeah? So that means 2 pi times 50. In another word, that is going to be 100 pi. Okay, so which one of these is 100 pi? Okay, so 100 pi t, yeah? So it is going to be, the answer is going to be either this or this one here, because these are 50 pi. These are incorrect, yeah? And remember this, what is one more thing to remember, we're given the effective difference, or let's say V effective, yes? But what we want is, remember, not I effective, we want the I maximum. So how do you do this one? You'll convert, you'll find V max using V effective multiplied by the square root of 2. Once you find this one here, of course, using the resistance equal to, let's say, V max over I max, yeah? Then, of course, you will find the current I max equals to what? equals to V max over R, and then of course you find I max. Then of course using this now you can plug into the equation and see which one it is, and then based on this you can choose the answer. So good luck trying this, huh? Of course it is easy enough. What about this one here? It says the power of a bulb is 60 watt and its effective value of the current is this much. What is the effective potential difference? Once again, regarding this, okay, because we have power, we have the effective current. It asks for the effective voltage. That is pretty obvious. So power equals 2. Remember the third equation of power. Remember I effective multiplied by V effective. So you have power and I. So of course you can find the V effective. Just make it the subject, divide the power you're given by the current, which is in this case going to be 120 volt by, yeah, it's going to be. All right, now let me give you an introduction about this one, and of course we're going to finish this one in next lesson, inshallah, but I'll just give you an idea, all right? So regarding this one here, next time we're going to talk about a pure self-inductance circuit. So you have a circuit basically with an inductance here, but remember this, every inductance can have a resistance with it as well. But when we talk about this one, we're just talking about if this circuit has only an inductance, okay? So if that is the case, then what would be the relationship between the instantaneous voltage and current? What would be the angle between the two? Like how will the ammeter and voltmeter would read us, for example, the moment that we turn the switch and all that, yeah? So, but all that is going to be for next time. So till then, keep practicing and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.